We are pleased to have Robert Mercas from the Loughborough University, who will talk about trying to do a counting of distinct repetitions in words.
Okay, thank you very much, Narad. And thank you everyone for being here, especially with the time difference and everything. I mean, Jamie's here, which is quite impressive. So what I will do today is basically talk about some work I did together with Szilárd Zsolt-Fazekas, who I think is also attending this. And basically, it's kind of annoying because it's the work we've been putting in for the last 10 years or so. And it all boils down to about one result, which is not even that impressive. But we hope that the idea of the technique that I'm going to present might be useful to someone, and maybe someone can solve this this conjecture, this whole problem that I'm going to talk about. So please feel free to interrupt me at any time. I'm trying to also look at the chat. It's going to be a bit weird because my presentation is on a different screen. I find it easier to do it like that. So I'm going to look a bit to the side. Hope it's okay. Yeah. So what I'm going to do is not actually prove any major result on counting distinct repetitions, but I'm going to talk about an approach we had and to give basically an overview of what is known about counting repetitions. And as usual, I'll start with some basics, some preliminaries, then I will present some basics, namely, I'm going to describe the setting that we created and the whole tools that we want to apply. Then where I'm going to talk shortly about our results, and then I'm going to present some final remarks. So some connections to other problems or that are kind of similar, but not really. In terms of basics, well, I have to explain what a repetition is, right? So using Jeff Shallit's website, you can find a lot of examples of repetitions. So hotshots is an example of a square, since you have hots followed by hots. Is an example of a cube, so a 3 repetition. Then you have also a 4 repetition there. And in general, a kth repetition is just k occurrences of the same sequence, put one next to the other. It's quite easy to understand. And then when you're going into counting, well, you're going to be able to look, for example, at the number of kth powers. And if you're looking at counting just squares, well, you have that in a word, you can have as many as a quadratic number of squares. And that's taking any unary word, what you will have is basically every even length factor will be a square. So counting them over and over, you have quite a lot. You can put a restriction on it and look, for example, at powers of primitive roots. So you're requesting that the word that is being repeated is primitive. And again, looking at squares, that there is a result actually from last year by Banai et al. That says that this number is bounded by n log n from above. So Frankel and Simpson actually proved that the Fibonacci word has an upper bound of almost 0.8 n log n. And then Banai managed to bring this down to n log n. And I think they used Linden roots to do this. Then the problem we are actually interested in is counting distinct powers. So what you want is, once you counted a square for a certain root, if that square appears again in the word, you just ignore it. So if we're going to take, yeah, I don't know, I copy pasted it from somewhere. So if I'm going to take this word over here, I have in it the square AA, for example, appearing over here. I have the square AA to the power 2 appearing here at the end. Oh, sorry, AA, you can also count here at the end. Then you have the square AABA, which appears, I guess, over here, AABA, AABA. You have ABA square, AB double A square, B double A square, and B triple A square. And these 7 squares are the only distinct ones occurring in this word. So there are quite a few, given that the word length is 13, so it's more than half, right? Good. So what was proven in terms of this? Well, first I'll present some words that I already said that this word has length 13 and 7 squares. What about the minimum number or a lower bound on this maximum number of squares? In their paper in '98, Frankel and Simpson actually introduced this problem of counting distinct squares, and they also gave an example of a construction which goes a bit like a zigzag. So what you do is you have powers of A's followed by a B, and you zigzag on them. So you have 1, 2, 3, and then you have 2, 3, 4, and then you have 3, 4, 5, and so on and so forth, right? Then you come 4, 5, 6. And if you're looking at this word, this, well, whatever length for this word, you will count unary squares, squares of this word, AJ, AK, BAJ squared, and you have AKB, AK plus 1 squared. So you have 3 types of squares that you're looking at. Then some years later, in 2014, Yonoshka, Mane, and Seki gave another example of a construction of a word which is rich in squares. And this, surprisingly, is very, very simple. Namely, you follow almost the same strategy, but instead of zigzagging, you're just increasing the number of A's. So you have A square, A cube, A fourth, and then you have only 2 types of squares to look at. And they show that actually the lower bound of the 2, I think that they match, namely it's 2k minus 1 over 2k plus 1 times the length of the word. So when I will count squares, I will always refer to the length of the word as an indication. Here, the K stands for the number of B's that you have in your word, and that's actually directly proportional with the square root of n. So it's relative to the square root of n. One of the main tools in proving these results on squares was the 3 square prefixes lemma. And this says that if you have a certain position in a word, 3 squares starting, namely you have that U is a prefix of V and V is a prefix of W, and all of U square, V square, and W square start at the same position, then you will have that for U primitive, you have that the lengths of U and V together are smaller than the length of W. So the largest of the squares will contain the smaller 2, right? So it will be way bigger than the smaller 2. And this basically is helpful in improving this bound in a way. This is what Ilie used in order to show somehow that you can get something of the sort 2n minus log n. But this basically brings me to what's the upper bound on the number of squares. So Frankel and Simpson proved that if you're looking at all of the number of squares that you can have in a word, then that is bounded by 2n. And they used actually this 3 square prefixes lemma for this. Then there are some direct proofs by Ilie, by Hickerson, and by Lam. These ones are earlier. This is a bit late and was done, I think, in a master thesis or something. And these are kind of direct proofs that use kind of the synchronization idea. And Hickerson actually just looks at the symbol that is falling on some position. Then the best known bound is 11n over 6, and it's by Deza et al. And the whole idea here was to use what they called FS double squares. So by using the 3 square prefixes, what you can show is that if you're going to look at the last occurrence of each of the squares that can appear in a word, when I'm talking now a square, I'm talking about a distinct square. So if you're looking at the last occurrence of each of the distinct squares, then at no position can you have more than 2 such occurrences starting. Yeah. So if you take any position, you can't have there more than 2 last occurrences of a square starting. And what Deza et al. Did is kind of bounded the number of of these positions where we have double square starting. And when they did this, actually, they used all kind of names for the squares, for these double squares that they had, fs double squares. Namely, they used alpha squares, beta squares, gamma squares. And what Thierry tried to do last year is actually use the same concepts of fs double squares and actually add a few more to them and try to prove a bound of 3n/2. So this is a paper which is on arXiv right now, and I tried to read, but I couldn't. So it's a bit the legibility of it is not yet there. So I hope that the author improves it, and then we can figure out if actually the bound is 3n/2, which would be quite amazing. A result by Mana and Seki in 2015 proved actually something really, really nice. Namely that if you're trying to count distinct squares, it is enough to do it on a binary alphabet. That is, you will not get the shortest word having a maximum number of distinct squares in it on a binary alphabet. But if you are able to get a ratio on the number of squares with respect to the length of the word on any alphabet size, then you can also get the same ratio on a binary alphabet. And their construction is constructive. So they do this constructively. And then with respect to distinct squares, there's also a paper of Amit and Gabrikovsky from 2017, which looks at circular squares. At distinct squares in circular words. So what they showed in this paper, which it's quite nice and uses some nice combinatorial properties, is that if you're looking at circular words, then the lower bound on the number of distinct squares is going to be at least 1.25, while the upper bound is going to be 3.14n. And I wanted to mention this one since I talked about some words that are rich in distinct squares, and I talked about upper bounds on the maximum number of distinct squares that a word can have, but I didn't say what the conjecture is. And actually the conjecture is that every single word will not have more distinct squares than its length. So basically for any word, the maximum number of distinct squares will be n. Okay. Going from squares, we can also look at runs. So what happened, Kolpakov and Kucherov introduced this concept and counted runs for the first time. And the run is basically like a repetition of a power at least 2, which you can't extend to the left and to the right. So if I'm going to consider this word, in this word, I have ABA as a run starting from the beginning. So I have ABA, ABA, and then an A here. And you can't extend it anymore. And you have that AABA is also run. So starting from position 3, you have AABA, AABA, and then an A. And this problem was introduced only a year later compared to the distinct squares, and was only proved that the number of runs, and when I'm talking about runs, I'm not talking about distinct runs. So you can count a run over and over again. It was proved that this bound is actually at most n by Banai et al. In 2014. And then the result was improved in the end by Holub to be 0.9482. And this shows that the bound is rather closed if you're taking this together with the result of Simpson from 2010, which gives the lower bound. So if you're looking at these two numbers, you see that, well, it's kind of there. It makes no sense to look further. The way that Banai et al. Proved this result was by using Linden roots, or some sorts of them. And I will get back to this a bit later when I will explain some of the strategy that we try to employ in our counting. Then there's also a counting of higher powers, but that's for integer powers. And there are some results by Crushmore et al. In 2010 that shows that for every power k greater than 2, you will have at most n over k minus 2 repetitions, distinct repetitions. So for cubes, you have at most n cubes. For powers of 4, you have at most n over 2 powers of 4, and so forth. And then Kubica et al. In 2009 actually proved that this bound, so the first paper is actually a bit earlier. This is the journal version. So they actually improved on this bound in the case of cubes. So they said that cubes are at most n over 2 minus something. The strategy for the second paper is actually quite technical, but for the first is rather easy. What they did is actually looked for every cube at the root of the cube and tried to show that you can't have two roots starting at the same positions. And here they were looking at the primitive roots. So that was really nice. So you can think also of Linden roots, for example. Good. That's about with my preliminaries. So if anyone has any questions about what I'm trying to count here, this would be a good time. So if not, I will just continue. Yeah. Hope I'm not speaking too fast. Okay. So what did we do? Well, we said that in order to count the squares, what we will do is actually do it by looking at suffix mountains. So we will try to separate the squares into groups that share a common prefix. And that is, we then will approach the problem and show that the number of squares in each group cannot be bigger than the number of occurrences of their common prefix. So if you're taking groups of squares, each sharing a common prefix, then for each of the groups, if you're looking at the shortest of the squares, namely basically which will be shared by all of the others, you're going to show that the number of occurrences of this one is bigger than the number of occurrences of this one in the word is bigger than the number of squares that you have in the group. And if you do this, basically you show that the number of all of the squares is going to be bounded by the number of occurrences of each of these, and therefore it's bounded by the length of the word, since every two occurrences will appear at different positions, right? And in our approach, we used only two results, namely the synchronization lemma, which says that two occurrences of a primitive, if you have a primitive word u and you're considering it squared, then within it you will only find two occurrences of u, namely as a prefix or as a suffix. And the second one is the well-known Fine and Wilf periodicity lemma, which says that if you have periods p and q and a long enough section, then you will also have the GCD of the two. I will not insist on these as they're probably both well-known. Okay, so I was talking about prefixes and trying to group them and whatnot. And what we did for this is use a concept that is very well known in stringology, especially. Yeah, so everyone dealing with string algorithms knows about suffix arrays. So what is a suffix array? Well, if you take any word, what you can do then is, well, you have an order on the alphabet and you can order its suffixes lexicographically. So you have that for this word, AAB, ABA, A is the smallest suffix lexicographical. Then you have AAB, ABA, so the whole word. Then you have ABA, ABABA, BA, and BABA. And then what I can do is actually look at the starting positions of each of these suffixes, and I get the suffix array. It's rather easy. And well, I was talking about suffix mountains, but why suffix mountains? Where is this coming from? Well, basically, if you're looking at the word again, what I can do is look at the suffix array of the word. And then for each of the squares that the word has, I can also look at all of the occurrences of each of its roots, right? So for example, for the square AA, sorry, here is not about squares, so it doesn't matter. It works also for squares. So I can look at the occurrences of A in the word, and I can, again, have them arranged lexicographically, the occurrences of AB and the occurrences of AA, right? So, sorry, suffixes starting with A, suffixes starting with AB, and suffixes starting with AA. And what you can see is that actually you can put these ones in some sort of mountain. So I have first all of the suffixes, then I have all of the suffixes starting with A. I have all of the suffixes starting with AA over here, and I have all of the suffixes starting with AB over here. So you get kind of a mountain structure if you put them one on top of the other. And I'm calling a cluster basically all of the suffixes that start with a certain word. So the cluster U is going to be all of the suffixes that start with U, and this is what I'm looking at. Sorry, maybe I should have started with this one. Okay, so suffixes starting with AA in this word will be the whole word, the suffix over here, the suffix over here, suffix over here, and suffix consisting only of A. Okay, and I think that this is more explicit. So I have a word over here. I'm looking at the suffix array of it. So, and then this is the suffix array of the word. So I'm ordering the suffixes lexicographically, and then I can put them into clusters. So I have all of the sequences starting with A, all of the sequences starting with AA, the one starting with ABA, AABA, ABAA. So this looks a bit like a mountain, right? Or a couple of mountains. Good. So what we did is we considered suffix mountains formed of words which are roots of squares. So basically in every word you will have a number of distinct squares. Each of these squares will have a root, and I can look at the clusters of each of these roots and see how these clusters compare. And what I will do in the following, I will consider that, well, what I will want to show is basically if I have a bunch of mountains, what I want to show is that the number of clusters that are building up are going to be in the end smaller than the length of the whole cluster at the base. So if I'm looking at this base cluster, then its length, so the number of occurrences of this this word within my main word, of this root within my main word, is going to be bigger than the number of actually distinct squares that have this as a prefix. If I can do that, then basically I prove the conjecture. If I can do it fully for mountains. And in the following, I'll consider a bunch of clusters that have the same size, and I will consider a chain of just consecutive clusters. So a chain can go from the top to the bottom or can just be intermediary, right? So when I will talk about the chain of clusters, I will talk about consecutive clusters, so to say. And here we have different clusters. Good. So suffix mountains are formed of roots of squares. And if I'm able to show that the cluster is bigger than the number of clusters on top of it, I'm done. So if this is true, then for squares, I'm going to be able to show that if I'm able to show that the base of the cluster is bigger than the clusters on top, then I have the bound of n. And if I'm looking at the problem in general, I have two goals. Basically, if I have a single chain, I want to show that the number of elements in this chain, so the number of clusters each on top of each other, is smaller than the base times a constant. And if I have multiple chains, I want to show that if you add all of these up together, they're going to be smaller than the length of the cluster here, times a constant. Why I'm using the constant here? Well, this constant basically will depend on the type of repetition that you're looking at. So if you're going to look at squares, this constant is going to be 1. If you're going to look at cubes, this constant will be 1/2. And in general, this constant will be 1/k minus 1. Okay. What we did in our work is actually prove this goal 1. We weren't able to prove goal 2. We have some ideas, but so far, no cigar, right? So some observations that are quite basic is that the set of suffixes with a common prefix are going to be contiguous in the suffix array. So that is, if you have a bunch of suffixes, each starting with AB, when you're looking at the suffix array, they will come one after the other. Then if you're looking at K powers, right, the cluster for the root is going to have length at least K. So if you're looking at squares, then each of the cluster will have length at least 2. And then if you're going to consider 2 clusters, what you have is that either one is fully contained in the other, and that's when the one containing, so if U contains V, then U is a prefix of V, or they are incomparable, and then the clusters do not overlap. So if 2 words are incomparable with respect to the prefix order, then their clusters are not overlapping. However, if their cluster, if the intersection of their clusters has anything in common, then either one is a prefix or one is a prefix of the other. Okay? So we have some really nice properties of clusters from this point of view. Good. So let's go into the results. The first of the results says that if you have 2 powers and the clusters of them are equal, then either one or the other of the roots is primitive. This is quite easy to show. So if 2 clusters have the same size, then either one or the other is primitive. So you have to think that U and V are actually connected, so one is a prefix of the other. So in that case, I either have U is the power of some primitive word, or V is the power of some primitive word. But what's very nice here is that the difference in between U and V will be less than that primitive word. So you have an extra prefix here, that T prime, that is going to be actually smaller than T, well, smaller or equal, okay? So you have whatever is extra in there, it's not too big. By using this fact, then, well, we can find out another result, namely that if you have 2 clusters that are equal, and again, U is a prefix of V in this case, then if I'm going to look at the rightmost occurrences of UK and VK, then their starting positions is going to be at least distance U apart. So the starting position of their last occurrences is going to be at the gap. Now, if you take this result, basically, and you use this previous lemma as well, what you get is that if you have a bunch of squares, such that there is a prefix order in between them, and their clusters are equal, then the length of the smallest of the clusters, or the largest of the clusters, the base cluster, is going to be at least K minus 1 times N. And that's basically because of this difference in between the starting positions at the end. Now, using this result, basically, you get the bound that I was talking about at the beginning, C times the length of the cluster for any power. However, this is for a really particular case, namely when the sizes of the clusters are the same. So it's not that impressive. So why did we choose to look at clusters and how are these connected? All of the previous ideas, as I said, they were looking at the last occurrence of a word. However, when you're looking at the last occurrence, you really lose control of what's going on before. And you lose control of how many times this appeared or how 2 words are connected later on. By looking at the cluster, we thought that you can bring everything together and therefore put some other bounds. And basically, the fact that by looking locally at any starting position, using the 3-square prefixes lemma, this might not be enough. So that's why our approach. So also another thing that we will try to do, or we try to do, is not count the whole squares. But what we did is actually count some really long prefixes of squares based on some properties. And the idea of this was not actually new, as, for example, in a paper of Jonoshka, Mana, and Seki, what they did in the lemma is show that you do not actually need the 3 square prefixes in totality, but you can actually subtract one of the last letters of each of the squares. So that's enough. And then I was talking about this result of Banai et al. With respect to runs. What they did there is actually associate each run with the Linden root of it, but the Linden root was taken with respect to a different alphabet order. So they were looking at different alphabet orders, and by looking based on the letter following this root, so to say. And then they were looking at the position of the Linden root and showing that for that certain position, you can't have more than two runs associated with one position. So what we did here is, again, look at some really long prefix and try to show that for every long prefix, we can associate uniquely a position. So how do we do that? Well, in order to do that, we define the representative of a square. So this is the longest prefix of the square that ends in this x. So the x representative will be the longest prefix of u square that ends in x. And I'll show an example just to make it easy. If I'm looking at this word over here, I have ABA square starting at position 7. So I have ABA. Okay? Now, the A representative of u square is actually going to be ABA, the whole word. And that's because the longest prefix of u square of ABA, ending in A is the whole word. So I have that the representative, the A representative is at this position. At the same time, I can look at the AB representative, and the AB representative is actually going to be at the beginning. And the AB representative of u square is the longest prefix of ABA square, which ends in AB. So it's going to be ABA. Okay? Good. So that's the X representative. And by using the X representative, I can get this word. So in UU square, you get a word of the form U prime X, where X is the representative, and U prime X is basically the longest prefix of U, which ends in X, right? And for this, you can define, well, the starting position of this representative and, so to say, the position where the X starts, or no, sorry, the position where the first U ends, the U prime starts. And then from this, you can define an X anchor. The X anchor will be actually the position of this X. So what I'm going to do next is, in every word, I'm going to look for the representative, and for each square, I'm going to look for the representative and mark the position of the X anchor, right? So for example, if I'm going back at the A representative, this was starting at position 7, and the anchor will be this A here at the end, at position 12. At the same time, if I'm looking at AB, the representative was starting at the first position, and the anchor will start on position 4. Okay? Hope I didn't lose everybody. So again, I'm looking at squares. I'm going to look at the longest prefix that ends in some word, in some prefix X. And then based on this, I can mark some positions. Now, for two square factors, U and V, so that U is a prefix of V, I can take a common prefix of theirs, right? What I'm doing in general, I'm considering chains. So I'm going to actually look only at one chain in this presentation. So therefore, if you have that u is a prefix of v, they obviously have a common factor. So I'm going to consider some x. Well, if the anchors of u and v coincide, then it will always be the case that u is a repetition. And furthermore, not only that u is a repetition, but you have that v has a prefix of the form t u prime x, where u prime x is that second part of the representative. And this is going to be helpful in the end. To prove this result is not actually very difficult. You have just a bunch of cases that you have to look at, as where the middle of v square starts, as compared to the start of the representative or the middle of the representative. And I will not insist on this, as it's not that interesting. Then, based on that result, we can prove the following corollary, which says that if you have two different chains, yeah, one chain of u's, one chain of v's, and you have that their roots are basically from the same chain, yeah, so I'm selecting them differently, and they have a common prefix, then if any two of these will actually be, or if you take pairs of them that have the same anchor, what you will get in the end is that there exists a common primitive word t that is a power of all of the u's. Okay, here I'm assuming that u's are smaller than v just to make it easy. So what this says is basically that if you're going to look at two separate chains that kind of interlace, if they at some positions, their anchors are on the same position, then what you will have is a primitive word in terms of which you can express each of these, each of the smaller of the squares that have a collision, so to say. Okay. I'm going to skip this. What you do is quite easy because you have these collisions. What happens is that you can express using the previous lemma, which I'm going to call collision lemma. You can express each in terms of a primitive word, and then you can look at the chains of the primitive words that you get, of the repetitions that you get. And then using fine and wealth, you get that there is a unique one for all. And from all of these points, we get our main theorem, which says that for any chain of squares, what you have is that the cluster of the prefix is going to be bigger than n, the number of squares plus 1. And I will explain shortly how we got this. So what we did is actually order in decreasing, so by taking decreasing order of length, each of the squares, we assign their anchor as a marked position. Whenever we have a collision at some point, we're going to consider the smallest of them. And we know that by looking at all of the smallest ones, they can all be represented in terms of a primitive word. Then what you get is basically a bunch of other squares that are all represented in terms of a primitive word. And what you do with them, well, you're going to look at the occurrence of this longest one from the ones that are colliding. You're looking at the first occurrence of that one. For the first occurrence of that one, you're actually looking at the prefix of it, namely the first half of the square. And in that half, you will mark all of the positions of the form ti of x. So you have these positions going from 1 to m, and you're going to mark all of the positions ti of x. And that's because you know that the longest one will have enough squares in it, namely m plus l, where m is the number of squares in the collisions, and L is going to be the index or the power in terms of this primitive word of the prefix that you're considering. And then what you have to do is only compare collisions of these extra points with collisions of normal anchors and show that it's falling in one of 3 cases and none of them is possible. So basically what we showed is that if you have a bunch of squares, each being a prefix of the other, then if you're looking at the number of occurrences of the smallest of them, it's going to be larger than the number of squares that you're considering. This doesn't work, unfortunately, for multiple peaks or different chains on the same mountain. And that's basically because you can't, if you're looking at the different chains, you can't use the fact that you get primitivity whenever you have collisions. And we actually have an example where you can consider this word over here and this word over here, and the anchor is somewhere in Z. So it's not really possible. So what you get in this case is a kind of a special structure that resembles the FS double squares of this et al. Then the optimality of this result from when looking at the number of clusters comes from the paper of Jonuszka, Mana, and Secchi, namely their construction. And we can show that if you want to show that if you have clusters one bigger than the other over and over, you can do it by taking a word like this. So you just take all of the UYs to be A, B to some power I minus 1. And you're looking at this, and what you will get is a word that has exactly as many squares at the base as total number of squares. And at the same time, you can get that all of the clusters are equal by taking words of this second form. And actually, this we will also use later on when proving a different result. As final remarks, well, using the second result of Jonuszka et al., what we can do is show that we can get all combinations of clusters. So if you're looking at clusters and you're trying to do squares, you can basically get kind of, or we conjecture that you can get anything. And the idea is that you can look at the difference in between the maximum length of a cluster and the length that it actually has, and then use a modification of this construction of the second construction that I showed on the previous slide and get these combinations. So for example, if I want to get clusters of size 7, 7, 5, 5, 3, 2, I'm going to look at the differences in between their maximum. So for the maximum for U1, I would need 7. Then for U2, I would need 6. So it's 7 minus 1, it's 6. Then 5, and so forth. And then I'm using the construction over here, namely having something like a to the power d, where d is the maximum of these distances, b, and then an index li. And I can get the word. So I get ab, aba, aba cubed, aba fourth, and so forth. And this word here will have exactly these numbers in terms of clusters of each of the squares. And the thing is, this construction doesn't render the word, the smallest word having such a structure. But we assume that if you actually can identify the smallest word having such a structure, then you might be able to tell more about the lower bound on the number of squares, at least. As I said, the proof for the Linden roots, for the runs was based on Linden roots. The issue with Linden roots when you want to look at squares is that multiple consecutive squares, and it was shown, for example, by Elia, that you can have a lot of consecutive squares. So almost like at every position you have a square. So if you're looking at multiple consecutive squares of the same length, they are going to be basically rotations of each other. Therefore, when you're going to look at the Linden root of them, they are going to have a unique Linden root. So you can't really associate a square with the Linden root. So therefore, there was kind of a totally different direction in between Linden roots and squares in general, in terms of approaches and everything. But what we showed is that if you want to look at runs, you can actually do that by using our strategy, more or less. So because we're looking at runs, and runs are powers of at least 2, what we can do is basically, for every run, we can consider the run ending square. So basically the last square that occurs in the run. And then, so for example, for the run AB, ABA, over here, the run ending square will be BABA. So what we can do now is basically consider for all of the runs, the run ending squares, and kind of use our strategy in order to put the bound on them. If I can put the bound on the run ending squares, then I obviously put the bound on the number of runs as well. Again, this will only work if I'm going to look at the cluster, right? So for the run ending square, I want for these to be, well, one prefix of each other. So the whole idea is that if you're going to look at runs, the first letter of each of these run ending square is going to be different from the one following the run. And therefore, what you can do is for every run ending square that exists, count two positions in the cluster of U, while in every other cluster that has U as prefix, one of the positions will be missing. Hence, when you're looking at two different run ending squares, U and V, you will have that the difference in between U and V is going to be at least K, where K is the number of run ending squares that you have. So that's actually quite a nice observation, and this gives you the runs result for a cluster, for a chain, quite easily. Unfortunately, this argument doesn't really extend easily to runs to more than 3 chains. So we think we have a solution for 2 chains, but for 3 chains is a bit difficult. In terms of closing remarks, since I'm kind of at the end of the time, what we did is we showed that the bound for one chain is n-1. And what's important to note here is that I'm never going to consider the lowest of the prefixes. So actually a prefix, the base of the mountain, but I can stop anywhere in between in this mountain and still get to the bound. And what we conjecture is that, well, quite naturally, the number of squares that you have in a word is going to be 1 over L-1, where L is the power of the repetition times the length of the word, or the number of occurrences of, actually, it's a bit stronger, is the number of occurrences of this factor in the word. We can actually generalize our square result for larger exponents, at least partially. And that's done by using K-1 representatives and anchor positions. And then, well, I already showed that we can generalize this for single chains of run ending squares. But still, the big challenge remains overlapping chains. And for this, it might be that we need a different definition, a slightly different definition of anchor, which basically depends also on the anchors that, well, of the squares that have this as a prefix, so to say. So if I'm looking at the anchor of V, I want to define the anchor of V based on the anchors of U, where U is a prefix of V, and so forth. And that's about it with my presentation. And thank you very much.
Oh, thanks a lot, Robert. Does anyone have any questions for Robert?
I lost everyone.
Francesco has a question in the chat.
So we didn't look at the different order at all. So I really can't answer that question. And the thing is, I'm not sure how you would do that. It's going to be weird because I'm not sure how much of the properties will be maintained. The whole idea with this suffix arrays is that you have this, they are contiguous, right? So if you're going to use different orders, they might shift all around. So let's see, Francesco, I'm not sure if that answers your question.
Gabriele, do you have a question?
Hi, Robert.
Hi,
yes,
Gabriele.
Thank you, Narad. How are you doing?
Good. Okay.
Thank you for the nice talk. Very interesting. Just a remark. When you were talking about clusters and mountains, That remind me suffix tries and classes of the suffix automaton.
So
Is there
already
any relation?
Dominic Koppel said that for him, this whole idea would sound better if you would think about suffix trees and so forth. But I can't tell you. We didn't look at that direction either. So I can't tell you anything about suffix tries or so. So we only looked at this way of putting them together by using suffix arrays. Maybe that's actually the wrong thing. That's the wrong approach that we're doing. And maybe we have to think differently. So maybe that would be an idea.
Okay, because the properties of clusters you showed at the end of the basic section are precisely the same properties that hold for the classes of the suffix automaton.
So I'm not sure how the automaton would help here, right? So, I mean,
no, I was thinking just in terms of the definition of the
these properties, I mean, they are quite basic. So it's nothing special here. It's just nice because you can actually put them all, you can combine them all, right? So one being the prefix of another, it means it goes on top. If not, they will just be separated, and then you can do the separate peaks, the separate chains within the mountain, so to say. But I'm not, I really don't know how to put it in terms of suffix trees, or I mean, I didn't think about it.
Okay, thanks.
Sure. Stepan.
Hello.
Hi, Stepan.
I have a side remark concerning your remark on preliminaries. You said that you discourage people from searching, from looking that these bounds are already too close. So for obvious reasons, I would like to advocate this research, and I think that it's actually quite exciting question whether the Jamie Simpson word is not optimal. So I don't think that it's just a boring research like hunting small numbers.
I didn't say it's boring research. I just said
that you said that it makes no sense to look for the optimum. So I think that there is a good chance that Jamie Simpson's bound is the best one. So I just want to recommend people this.
Okay. So I apologize if I offended you in any way, and I didn't mean this. You're right. So I feel like that problem is so close that if you're going to make progress, you're going to be really dedicated to it. Yeah.
Exactly. But the point is that you can find the optimal bound.
Yeah. But for the squares, there's a lot left. So Stepan, you can work on squares now that you're done with rounds.
I agree.
Are there any other questions?
There is a remark of Francesco.
Yeah, I can see that. I don't know Francesco, so I can look into it. I have no idea. I didn't think about any other type of order.
Anything else? If not, I'll just say thank you to Robert again.